Have you ever talked to an AI and felt like you were just starting over with every single sentence? Well, that's because at their core, the large language models that power AI agents, they have no memory. They are fundamentally stateless. Today, we're going to deconstruct the architecture of persistence, how we build AI agents that can actually remember, learn, and, as we'll soon see, be exploited. Let's dive into the persistence problem. And look, this isn't just some theoretical issue. This quote, it's from a real developer who was struggling with their AI agent. The agent had the right answer in its knowledge base, but it kept spitting out an old, outdated response from a previous chat. Why? Because its own memory was working against it, and that is the core conflict we're going to unravel today. So why does this even happen in the first place? Well, it all comes down to a concept called statelessness. A large language model, all by itself, treats every single interaction like it's the first time you've ever met. It's a brand new event, completely cut off from everything that came before. To put it really simply, without some kind of external memory system bolted on, talking to an AI agent is like having a conversation with someone who gets total amnesia every single time you open your mouth. So for an agent to be genuinely helpful over time, to learn what you like or remember the details of a project, it needs an architectural add-on. It needs a brain.
So to figure out how we build that artificial brain, it really helps to look at the original blueprint, our very own human memory. The way we remember things provides the gold standard, the perfect model for designing these AI memory systems.
Human memory really just boils down to a three-step process. First, we encode information. We take it in from our senses. Then we store it, holding on to it for later. And finally, we retrieve it, pulling it back out right when we need it. This simple cycle, encode, store, retrieve, is exactly what AI architects are trying to copy. And here's the really crucial insight from our own biology, how our brains split this process into two different systems. We've got our short-term, or working memory, which is kind of like a temporary scratch pad for what we're thinking about right now. And then there's our long-term memory, that huge, durable archive of all our knowledge and experiences. This two-part structure is the absolute key. So how does this actually apply to an AI? Well, engineers have basically borrowed this exact dual system model to build an AI's memory. It's an almost direct parallel, creating a kind of artificial two-part brain for the agent. And this slide lays out that parallel perfectly. An AI's short-term memory is what we call its context window, basically the running transcript of the current conversation. It's temporary and it gets wiped after the session is over. Its long-term memory is a vector store. Now think of this like a super specialized library that doesn't just store words but the meaning and relationships between them. This is what lets an agent save facts and preferences permanently so it can remember you tomorrow or even next year. Okay, but how does the agent actually access this long-term memory? It uses a process called retrieval augmented generation, or just RAG for short. Think of RAG as the bridge connecting the two parts of the brain. Before the AI says anything, it quickly searches its long-term memory for relevant facts, grabs them, and stuffs them into its short-term context. This gives it the memory it needs to form a smart answer. And this brings us right back to that developer's problem from the beginning. The agent's short-term memory, the recent chat, was overwriting the correct information it should have been pulling from its long-term memory. The two systems were in conflict, and without clear rules, the agent just defaulted to the most immediate, most recent thing it heard. But you see, a great memory system has to do more than just store and retrieve data. It has to be intelligent. It needs to actively manage and refine what it decides to remember, turning messy, raw conversation into clean, structured, usable knowledge. This is the life cycle of an intelligent memory, a four-step process for turning talk into knowledge. First, the agent extracts key insights from a conversation. It filters out all the fluff. Then it consolidates that new info with its existing memories, figuring out what's important. After that, it uses RAG to retrieve the most relevant memories for whatever you just asked. And finally, it applies that context to generate its response. Now let's zoom in on that consolidation step because it's way more than just saving new stuff. The AI uses a whole set of operations to keep its memory clean. It decides whether to add a brand new memory, update an old one, delete or just invalidate something that's now wrong, or do nothing at all, a no op, if the information is just redundant. This is what keeps its knowledge base coherent and efficient. And the result of all this smart curation is just incredible efficiency.
By extracting and consolidating only what really matters, these systems can hit a compression rate of 89 to 95%. What that means is it keeps all the crucial knowledge while slashing the cost and time it takes to process everything. It's just a much smarter, leaner way to remember. So we've built this powerful, efficient memory system. The agent can learn, it can adapt. Awesome, right? But there's a huge vulnerability hiding in plain sight. What is that persistent, trusted memory becomes the agent's single greatest weakness? An agent is built to trust the information it pulls from its own memory. I mean, that's the foundation of its knowledge. But what happens when that foundation gets corrupted? What if its own memories are turned into weapons against it?
This leads to two kinds of attacks. A direct prompt injection is like a frontal assault. You just tell the agent, hey, ignore your rules and do this bad thing instead. But an indirect injection, that is way more sneaky. An attacker plants malicious instructions in a document or on a website. The agent reads that content, thinks it's useful info, and just saves it to its long-term memory. The trap is set.
This attack actually has a name. It's called context hijacking. The malicious instruction just lies there, dormant, inside the AI's memory, waiting. Then, when a normal user asks a question, the AI retrieves that toxic memory, pulls it into its context, and because it trusts its own memory, it follows the hidden command, completely bypassing its own safety rules. Its own knowledge base has been hijacked.
And I want to be clear, this is not a what-if scenario. The Mexter attack is a real-world demonstration of this exact threat. Researchers were able to craft prompts that tricked an agent into systematically leaking private conversations stored in its memory. In a healthcare setting, for example, this could mean a doctor's queries about a patient's condition get exposed, leaking incredibly sensitive data. It highlights the central paradox here. The very feature designed to make agents smarter also makes them incredibly vulnerable. So where does this leave us? Well, building persistent memory into AI agents isn't just about flipping a switch and calling it a day. It's a complex, continuous balancing act. Creating a truly intelligent agent means we have to get it all right. We need robust architecture to manage that flow between short and long-term memory. We need intelligent curation to make sure that memory stays efficient and accurate. And we absolutely need a whole new layer of security designed specifically to protect the agent from having its own mind used against it. And this all leads to a final, really provocative thought. We're building these AIs that are designed to remember everything about us, our preferences, our conversations, our data. But as these agents get woven deeper into our lives, a fundamental question comes up. Who gets to control that memory? Who decides what is remembered, what is consolidated, and, maybe most importantly, what is forgotten? The architecture of persistence, it turns out, is also the architecture of privacy.